to look at ways that we could maybe rebuild courses or give you guys tools or study tips and things just to make it easier for you guys. So the whole aim is really just to decrease anxiety so that we can try and make your performance a little bit better. So all I'm going to do is just pass out just a few slips of paper to each of you that just has the internet URL code that you guys can go to just to fill out the survey if you want. It probably takes about 15 minutes or so. And then if you're in the experimental group, it's just a short 5-minute, 5-question questionnaire that you get every 2 weeks on top of the initial questionnaire. Okay? So I'll just pass that around, and that's about it.
There's no anxiety in this class, right? All right. So everybody say hello to YouTube. Hi, everybody. Hi. I know our numbers here are dwindling. I assume everyone's at home watching live. Okay. All right, so let's point towards the thingy. Can you see the screen, YouTube people? Excellent. We're passing around some stuff. Hang on. We haven't started yet, don't worry. Your audio's not broken. No problem. Okay, shall we begin? So I had to talk to the YouTube audience while you were doing that thing, so they don't think that the thing was broken. All right, so today we're moving fast these days. We're not lingering on old topics, moving on new topic. So today we're doing this thing called ANOVA, which stands for the analysis of variance. Has anyone heard of ANOVA before, or ANOVA? ANOVA, 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 ANOVA. No, yes, no, good. So if you go into psychology, which is a fake science, it's a fake science with real methods. If you go to psychology, they're really big on ANOVAs, and lab science as well, huge on ANOVAs. I did my first ANOVA during my master's degree, which is in neuroscience, and I didn't take stats ever in my life until my PhD actually. So I was like, and we didn't have the internet back then, no internet. That's how old I am. And so I had to look up a textbook. How do I do this? And there's ANOVA there. I'll do it. And I thought it was fine. And when I became a statistician, I looked back and realized that was nonsense. Not just my methods, but the application of it. And so much of the application of ANOVA is nonsense when it's in the field, because the sample sizes aren't large enough, or people don't understand independence versus dependence, or what a nominal variable is versus a ratio variable, and things like that. These are nuances that you are learning here really are in many ways far beyond what we actually see in some labs, where they just look up, I do this analysis and plug in these numbers and see what I get. But there are assumptions that go into them. So the ANOVA is a derivation of the t-test. And as you move through your career, you will, if you're going to get into psychology, for example, the fake science. Sorry, I have psychologist friends, and it's my reflex now to always call them fake scientists. And they are. And then the ANOVA is the go-to analysis, so it makes sense to pay attention to it today. There are 3 different kinds of ANOVAs. We're only going to do one manually, but I want you to know about the other 2, obviously. So let us begin with a bit of review. I just realized I just called psychology a fake science on the record. Right, so people can now listen to it live around the world and think, Dio Nannon thinks psychology is a fake science. And it's true, I do. So, so we looked at the t-test previously, right? So in the t-test, as you are now experts in, I assume, because you've done all the readings and the exercises and you paid attention so thoroughly in class. In t-test, we were comparing the means of 2 different samples, or the means of one sample to an external value, right? Now, when I talk about this kind, there are 2 different types. What are the different types of this kind from the 2 samples? Do you remember? 2 different scenarios. It's only been 2 days. Yes, ma'am? And what's the difference? Yeah? That is correct. So for those on YouTube that can't hear what you said, she says there's an independent and dependent. That's correct. The independent has two different samples of different people, and the dependent either are the same people being tested twice, or people with a systematic relationship to one another, like spouses or twins. And of course, there's the mean comparison to an external value. Those are t-tests. What happens, though, if we want to compare the means of more than two things? You can't do that in a t-test, as I hope is obvious to you when you go through the math and realize how we did the math last time. I'm subtracting two different things. I can't subtract three things from each other. There's no way to do that. So we need a new technique to compare the means of three different things to one another. And that technique is the ANOVA. Now, if I didn't teach you the ANOVA, and I ask you to figure out if the mean ages of these three different classes of stat students are different, what technique would you use, given what you already know? We only know one technique, a t-test. So is there a way to apply the t-test to figure out if these three classes are different? Knowing that t-tests can only compare two of them at a time. Hint, hint, hint. Yes? Exactly. So just compare three different pairs, right? First two, second two, and 1 and 3. Yeah, that's the obvious way to do it logically. We could do that as well. But this is kind of like a time-saving step in one scenario only. So we're talking about the analysis of variance. I call them ANOVAs. Some people call them ANOVAs. Caribbean and Caribbean. By the way, it's Caribbean. It's not Caribbean. You can tell that to your friends. So, like I said, we use it to compare group means when the t-tests are not appropriate, i.e. when there are more than two groups being used. Great. So there are three different types of ANOVA. There's one-way, two-way, and n-way. Guaranteed. Some people are going to mix these up. Guaranteed. Even though they'll be clear today, in the moment of stress in the exam, you're going to mix it up. Oh, I got a question about the exam, obviously, because everyone has questions about the exam. And it's not until after the midterm, right? That's right, right? I get my classes confused all the time. It's after the midterm, yeah? Sorry, it's after reading week. After reading week. Okay, so we got some time still. So, yes, I allow this class to have a so-called cheat sheet for the midterm. And that's an inappropriate term because you're not cheating if it's allowed. It's a resource document. How's that? And what it is a single 8.5 by 11 page on both sides with whatever you want on it. Printed, written, microdot, letters from your mother, cartoons, I don't care. Photocopy the textbook if you want. Shrink it down, I don't care. It's not going to help. It's there for you to write down formulas or, inspirational quotes. I have no idea. So don't worry about memorizing things. Worry about understanding and applying things. And we a calculator too, because why not? I don't care what kind of calculator. If it's a graphing calculator, what are you going to do? Program more stuff from your cheat sheet? It's not going to help. So just do exercises. Okay, moving on. Am I scaring you? Good, good, it's good. All right. So the one-way ANOVA is when we compare. It's like the t-test scenario, except we've got three different groups. We've got one nominal variable and one continuous variable. All right, so one independent variable and one dependent variable. And that independent variable could have any number of levels. For example, a car company with 3 factories. Is the mean mileage of cars produced by each factory the same? So in that example, what is the independent variable? It stares at me blankly. You gotta get this. What is the independent variable? Hint, the independent variable is always the nominal one. Yes? The car factory. How many levels? How many possible values are there of that particular variable? What can that variable be? For example, if your variable is age, you can be 1-year-old, 2-year-old, 4-year-old, an infinite number of numbers. If your variable is car factory, how many levels are there? Yes? Exactly. All right, keep that straight in your mind, because suddenly you'll see that question in an exam, and I'll ask you, what kind of ANOVA is this? And you'll say, oh, it's a 3-way, because there are 3 different kinds of car factories. No. There's one independent variable, and that's car factory. Okay, and you have one dependent variable. What's the dependent variable? The mileage, exactly. So in the case of t-tests and ANOVAs, the dependent variable is always the continuous one, and the independent variable is always the nominal one. Okay, so straightforward. One way ANOVA, ANOVA, Caribbean, and it just looks like a t-test except 3 different categories. Again, only one nominal level though. Now a two-way ANOVA is an additional dimension of complexity. So the example here is that a car factory produces the same 3 models of cars. And we want to know, do the mileages vary across the models and the factory simultaneously? Getting complicated, right? So what are, in that case, there are 2 independent variables. What are they? Yes?
The factories and the models.
And the model, exactly. How many types of models are there? 3, precisely, okay? It's still a two-way ANOVA. It's a two-way ANOVA because there are 2 nominal variables, 2 independent variables. It's not a 3-way because there are 3 different models of cars. It's a 2-way, right? So they differ in that the number of groups have a number of independent variables is what determines it. We have this thing called N-way now. Now consider I'm comparing different factories of cars, 3 different models of cars on 7 different continents, made in 10 different years. I want to compare the mileages across all 4 of those dimensions: factory, continent, model, and year. Right? So I've got 4 things happening simultaneously, 4 categorical variables, 4 nominal variables: factory, continent, model, and year. Right? That's an N-way. N could be any number of things. Okay. So 1-way, 2-way, N-way. We haven't got a 3-way, really. We don't call it 3-way, it's N-way. So again, that it's the determining factor in determining which kind of ANOVA it is the number of independent variables. So always ask yourself that question first. How many independent variables do you see? Okay. In this class, we will only do the manual computations for the 1-way ANOVA, but I want you to know when we would use a 2-way or an N-way, simply by counting the number of independent variables. So, if I'm comparing the mean bacterial count in 4 samples of milk, it's on the slide already, what kind of ANOVA is that? Shout it out. It's on the slide, shout it with me. You can do it, shout it. Ah, 1-way. You're not shouting to me, what the hell? Okay, so what is the independent variable in that one? No. There it is, milk. So the types of milk, right? 4 samples of milk. Sample 1, sample 2, sample 3, sample 4. That's the independent variable. The dependent variable obviously is bacterial count. I'm comparing the mean weight of men versus women among Canadians and Americans. Okay, that's obviously a 2-way. So what are the independent variables in this one? Yes, ma'am?
The gender and the nationality.
Precisely, you said it precisely right. Gender and nationality. Okay. Now, some people read that and they see, oh, there are 4 independent variables: men, women, Canadians, Americans. No, there are 2 of them: gender and nationality. Gender happens to have 2 levels. Nationality happens to have 2 levels. You have to keep those things straight in your mind. What's a variable and what's a level or a potential value? Lastly, the mean price of 6 categories of vegetables in 4 different grocery stores in 7 different countries. Obviously, that's an N-way. What are the independent variables here? Yes, that's right. That is correct. Right. So once you got more than 2, it's an N-way. Right. It's not hard, but come exam time, you will get it wrong because you'll freak out. Right. So get your freak out done now. So again, dependent variable is the integral ratio level thing, like the mean weight, the mileage, all those things. Bacterial count. Independent variable is a nominal level. Sometimes we use ordinal, like for example, we can look at the mean ages of people who are normal weight, overweight, and obese. We can rank normal, obese, and overweight, or we can think about them as nominal. So it's not unusual to use ordinals in lieu of nominals for ANOVA. Okay, when we are phrasing the null hypothesis for our ANOVA, what we are looking at, remember the null hypothesis for t-test? What was it? If I'm determining whether or not the mean age of this class is different from the mean age of that class, what's my null hypothesis? Yes. That they're the same, exactly. My mu's are the same, right? So that would be like that equals that. For the ANOVA, they're all the same. So all of my samples are going to be the same. So if I'm comparing, again, those 3 car factories and whether or not the mileage and all the cars produced are the same, it would be car factory 1 equals car factory 2 equals car factory 3. Okay? Or there are 4 car factories, it's across there. The alternative is going to be weird for you. The alternative hypothesis is just not that. And we can phrase it like that, not that. Now, there's a reason for that. There's a reason I phrase it that way and not that doesn't equal that, doesn't equal that, doesn't equal that. So if I were to put unequal signs here, do you see how that is a very specific scenario? Right? It's possible, for example, for these 2 to be equal and the rest of them not to be. And it would still be not that, not the null. It's possible for these 3 to be equal and that one to be different, and that would still be an alternative being true. So all we care about is, are they the same or are they not the same? If one or more of them is different from the rest, then the null is rejected. Okay? So the important observation there is the ANOVA doesn't tell us which one is different. It just tells us whether or not they're the same. So if I reject the null, I know someone's sticking out. I don't know which one it is, but somebody's not the same. One of these things is not like the others. Right? So let's say I was comparing, again, the mean mileage of 3 different car factories. And my null is going to be car factory 1 equals car factory 3, etc. And my alternative is not the null. And I managed to reject my null hypothesis. So I know that one of my car factories, at least one, is not like the others. How can I now test to see which one it is? Knowing what you know now, given the skills that you currently have. Yes?
Do a t-test between each of the 2 variables together.
That is correct. That's correct, absolutely. So there are other ways of doing so, but the skill that you have now is you are now empowered to do a t-test if you wanted to, which defeats the purpose of having done the ANOVA in the first place, but there you have it. Okay. Now, like all things, we have some assumptions when we do an ANOVA. The first assumption is there's random sampling populations, meaning that the cars that I select for my sample weren't tailor-picked from the factory to be the best mileage ones, just randomly selected. The second is the dependent variable is normally distributed. All right, so again, that's the mileage or the age or the bacterial count that in general is going to be shaped like this. I don't know if it is. Just like in the t-test, I didn't know if it was. But we're going to do some things that allow us to assume whether it is or not. And the variances are going to be equal. We call that the homogeneity of variances. Remember, for the independent samples t-test, we had the same problem. We had to determine if the variances were the same in both of those cases. And to do so, we tested with Levine's F-test. We can do the same thing with ANOVA. We can run Levine's F-test to determine if the variances are the same or not. So, robustness is a word that pops up a lot. With robustness, we mean we can forget. If something is robust, then the assumptions are fine. We can assume that the assumptions are great because these other characteristics kick in to tell us that everything's great, all the scenarios we can use. So the robustness of the ANOVA is we can say that it's normally distributed if each of my groups has at least 20 people. If it doesn't have at least 20 people, then I can run my tests for normality like we did last time, the Kolmogorov-Smirnov or other kinds of tests. But in general, we like to have at least 20 people in each group. And the examples we'll do don't have 20 people in each group. So clearly we can't assume they're normal, but we do anyway, wink, wink. But recognize that that's an issue sometimes. And we like to have the n's, the number of people in each group, number of samples in each group, number of cars in each group, number of bacteria in each group, etc., roughly the same. Is there a rule of thumb? Yeah, no more than 1.5 times more than each other. Right? So if one of them has dramatically more numbers than the other ones, then some things may not be normally distributed. So, but if these things apply, then we're probably okay. So, before we actually do the test, we have to talk about something called partitioning of variances, and this is how the ANOVA really works. If you think about comparing, okay, let's do the car example. Let's do 3 different factories of cars, each making the same kind of car, and we're comparing the mileage in each factory. The ways in which our numbers can vary are two different ways. So what's the first thing you think about in terms of variation, in terms of, I don't know what the word I'm looking for, fluctuation in numbers? What are some of the characteristics in that scenario that would concern you? How might the car mileages vary and why, if I'm comparing them across different factories? Yeah? Distance is one thing, sure. What else? When you buy a car, you ever think about what determines this variance? What determines this mileage? Is it just the make of the car? If you and your friend have the same model, have the same mileage, yeah? Fuel economy, sure. That's a characteristic of the model, but there's been all other things. So really the categories come down to two things: characteristics of the factory and characteristics of the individual cars. How are they made, and individually how they turn out. So in other words, there's variation between the different factories. Maybe this factory has better employees, this factory has better, I don't know, pension plan, I have no idea. The workers are happy, this one has a different age distribution, so they're working better. Or within my group of cars in each factory, maybe some of them are crappy and some of them are good. So there's variability within each factory, and there's variability between each factory. So if you're talking about people differ because there's individual variability. For example, if I'm looking at your test scores, the mean midterm marks between this class, the other class, and a third class. Within each class, there's going to be people who are different and the same, and between each class, there's going to be differences in teaching styles and things like that. So the terms between and within keep coming up all the time. Between group variation and within group variation. Okay? So within each group, there's going to vary. So in this room right here, if I'm measuring your test scores, maybe I got some geniuses, maybe I got some dumbasses. I don't know. Right? I probably got both. Which one you are, I'll find out soon. Right? And in the other class, I'll have some of those as well, but there'll be different kinds of ones. But again, maybe the scheduling of the classes also matter. Maybe the nature of the professor will also matter. Maybe the time of day will also matter. So we have to account for both kinds of things, between and within. So again, between group variance is when the differences between the factories, between the classes, and within is amongst the students, amongst each of the cars, or the differences. Am I overstating that case? I've said it enough times, hopefully it's clear, right? So like I said, the ANOVA is an extension of the independent samples t-test. Independent samples t-test holds that we have two unrelated groups that we're comparing, and the ANOVA is three unrelated groups that we're comparing. There is a version of the ANOVA that compares related groups or the same group, and we'll talk about that later on. But right now, put that out of your mind. So one of the things that we have to do first when we compute the ANOVA is we have to have this concept called the grand mean. So if I am comparing the mean marks of this class versus another class versus a third class, each class has a mean mark, and all together you have a grand mean. All right, so add up everybody in all three classes and divide by all 300 students, get a grand mean. So that's important to know as well. So much like our previous tests, our t-test we computed a t-statistic, and our z-test we computed a z-score. With the ANOVA we're also going to compute a new kind of fancy score, and that's called the f-statistic. You've already seen a version of the f-statistic called Levine's f-test. It's a similar kind of f thing. So we're going to compute the f. All right, so, oh, interesting. You've already seen the f-test, so it's kind of the same. If this isn't that important to you, but know it theoretically, much like the t-distribution, remember the t was a version of our normal in which the more numbers I had, the higher and tighter it got. The f is the same thing, except I square the t. It's just the t squared. It's fascinating. That's not going to be useful to you in any way, shape, or form, except that now you know it theoretically, and you can show off to statisticians you might meet one day. Did you know the f is a t squared? Oh, you're clever, and you impress a dork. That's great. So the f statistic is also an f ratio because we're dividing the two variances we talked about. We're going to divide the between group variance over the within group variance. So the amount of splay I have between my factories is going to be divided by the amount of variation, width, and splay inside the factories. And that ratio will tell me my f-test. Obviously, with all ratios, there's a magic number. What's the magic number with ratio? 1, exactly. So it tends to be symmetrical around 1. That means if there is no effect, if the null is true, if the independent variable has no effect, then over the long run, our f statistic should run towards 0. 1 towards 1, sorry, 1. Okay. So another way to look at it is, if this helps at all, is the f ratio is the effect of the independent variable. The independent variable is the category, which class you're in, or which factory is making the cars, plus some kind of error from how I chose those groups, how I chose this class, how I chose the factory, divided by the overall sampling error. Again, that's more complicated for you. Forget that and think about the variances. Variances works fine. Right. So, much like our t statistic, once we compute our f statistic, which we will, we also have to compute our degrees of freedom. That's that annoying term that's going to haunt you for the rest of your statistics career that probably you won't have a full understanding of because no one really does. So degrees of freedom is, think of it as a proxy measurement for the amount of things in my sample. The amount of car factories and the amount of cars, the amount of stats classes and the amount of stats students. So some kind of mathematical expression of how many people I have to work with, how many samples I have to work with. That's my degrees of freedom. When in the ANOVA, we actually have 2 degrees of freedom we're going to compute. We're going to compute degrees of freedom for within and between, again, within and between. And there's separate formulas for both of those. Once I have my degrees of freedom and my alpha level, I can go to the back of the book and I can look up, much like a t statistic, I can look up the f statistic and compare it to my f statistic. Got that straight? Just like a t-test, except instead of computing a t, we're computing an f. And we're computing the degrees of freedom differently. We'll do an example. Okay, so here is the differences again. Degrees of freedom between is going to be the number of nominal categories minus 1. What does that mean? So if I'm comparing the mean marks of 3 different stats classes, how many independent variables are there? Just one. It's one way out of it. What's the independent variable? I'm comparing the mean mark in 3 different stats classes. The stats classes, exactly. Now, how many stats classes are there? 3. That's the number of nominal categories. That's the number of items in my independent variable. Minus 1 is my degrees of freedom. Now, my degrees of freedom within is going to be the total number of subjects minus the number of categories. Wow. So again, if I have 3 different classes, and I'm comparing the mean marks of 100 students in each of them, I have a total number of students of 300. And if I subtract the number of classes, which is 3 from 300, that's my degrees of freedom within. Right? And that's the summary for it here. So K is the number of levels of my independent variable, the levels. Again, if I've got 3 different car factories, there are 3 levels. 1 variable, 3 levels, so K is 3. If I've got 7 different types of vegetables, there's only 1 variable, vegetable type, but 7 levels, so K is 7. And degrees of freedom within is the total number of things that I have minus the number of categories. All right, that's going to confuse you for a bit. We'll run through an example and see if it's clear. All right. Example, mean grades in 4 different classes. There are 100 people in each class, so my K is going to be 4, my N is 400, and so my degrees of freedom between is K minus 1, or 3, and degrees of freedom within is N minus K, or 396. Straightforward stuff. Again, grade 3 math. You just got to be able to identify the numbers from the question. So, if I now take this information and I go to the back of the book, to page 413, or to an online F calculator, which is always an option, and I look up what the F cutoff is for an alpha of 0.05. And again, it doesn't have to be an alpha of 0.05. It could be an alpha of 0.01 or whatever we want, but usually it's 0.05. What is an alpha again? What's the official name for the alpha? Type 1 error, exactly. And if my p-value is less than alpha, what do? Yes. I reject the null, exactly. If P is low, the null must go. Precisely. Good. Remember all that stuff. So reject the null if the F from the table is less than the F that you calculated, like last time. So like a t-test, if my T is bigger than the book's T, then I reject the null. If my F is bigger than the book's F, I reject the null. I always want my thing to be bigger, because bigger is better, right? Good. So like everything else, we have online calculators. I think these still work. You'll try these online calculators as well. So before I do an example, we have another concept you have to think about, and this is the sum of the squares. Sum of squares will come back to haunt us later on when we do linear regression. So the sum of the squares is the sum of the squared deviations. What's a deviation? Remember that word? Remember the standard deviation? What's a deviation? Good thing it's a cheat sheet, huh? What's a deviation? You remember this? Yes? Is that a hand? Yes. Exactly. It's a fine guess. Right? And if you got it wrong, I'd mock you incessantly. No, it's fine. It's good for you. Right. So, so every one of my data points, if the distance from the mean in that group is a deviation. If I square those deviations, why would I square them? Yes? To get absolute values, to get rid of the negative, because some are going to be less than the mean, some are greater than the mean. I care about the distance from the mean, so I square that to get rid of that minus the negative number. And I add up all those squares. That's the sum of the squares of the deviance. So if you think about what that means is, in this class, for example, if I care about your mean mark, I look at your mark, and it's detracted from the mean, I get a deviation. Your mark, stuff from me, I get a deviation. And I get everyone's deviations, and I add them all up. That's some kind of measurement of the average splay, variability, width, variance of marks in this class. So that's what this is. It's an attempt to quantify the amount of spread of my data. Right? So there are two kinds of sum of squares here. There's the sum of squares within, between again. So between is obviously between the different groups, between the car factories, between the different stats classes. So there's the mean mark in this class, the mean mark in that class, mean mark in the third class, and the grand mean. So how different is that mean mark from the grand mean? How different is this mean mark from the grand mean? So I got those deviations. That's my between group deviations. And within each group, I have deviations too. So within this class, each of you is different from the mean. So that's my within group deviation. So I'm going to sum up the squares of the deviations between the groups and sum up the squares of deviations within the groups. And I plug them into this formula. Yes, ma'am? No, the grand mean is for everybody. Right? So again, there's going to be a deviation scores within each group. So let's say there are 3 classes. I'm going to have deviations in each of those. 3 different measurements of the amount of deviation and a large deviation measurement for everybody. Okay, we'll go through an example so it'll be clear. So this is a formula for completing F using this concept. Right, moving on. Step 1 is we're going to calculate the sum of squares. Sum of squares within, like I mentioned, a sum of squares between, within each group and between the groups. Okay, and then the mean square is the average. So the mean sum of squares is obviously the average sum of squares. I'm not going to define average for you, what average means. Right, and so this is the other way of thinking about the statistic. So I mentioned before, it's the sum of squares divided by degrees of freedom. That's the same as this. The mean square is the sum of squares divided by degrees of freedom. Like I said, once you've got that, you compare your number to the back of the book, and we decide whether or not to reject the null. Right, here's the example. This is the example from the textbook, because I was lazy, right? So we have randomly assigned 15 myocardial infarction patients. What's an infarct? Heart attack, exactly. Heart attack patients to one of 3 different therapies: music therapy, relaxation therapy, and a control group. And after each therapy, we measure their stress from 0 to 10. What is the independent variable? Yes? Exactly, the therapy group. And how many different kind of therapy groups are there? There are 3. Okay? Those are the levels. 3 different levels, 1 dependent variable. And what is the dependent variable? Stress score, exactly. Perfect. So first step is to get the data out of the question. And it's not unseen for some asshole professor to ask a complicated question from which it's difficult to extract data. I don't know who would ask such questions, but it's possible. Okay, so we want to know, is the mean stress of individuals different between these different groups? So the first thing we're going to do is we have to figure out the analysis. It's a one-way ANOVA, obviously, because I said we're not going to do anything else. So that's a giveaway. But why is it a one-way ANOVA? Yes. Exactly, only one independent variable, which is, again, yes, the therapy group. Perfect. Okay. The null hypothesis here is going to be, are the means the same? It's always the same. Is the mean stress score for therapy 1 equals to therapy 2 equal to therapy 3? And the alternative is going to be not that. It's probably the easiest alternative hypothesis to ever write. Not the other thing. Good. Moving on. Why is that not moving? Moving on. Okay. What are K and N? So how many levels are there in the independent variable? 3. So K is 3. How many subjects do we have? 15 subjects. So degrees of freedom between is going to be K minus 1. That's 2. And degrees of freedom within is going to be N minus K, which is 12. So 15 minus 2 is 12. So far, so good. Okay? That's pretty straightforward. Next thing we do is we set up this table. These are our data. Okay? Much like the independent samples t-test, the data looks like a spreadsheet. So here is group 1, group 2, and our control group. Here is person number 1. Thought, oh, I didn't give me, that's like, I got 0 stress. That's fantastic, right? And this guy here, but this guy was really stressed out from the first music. That's horrible, and so forth. And this guy was, oh, I got no stress at all from group 2. And this guy, oh my God, this group 3 music is just stressful. Whatever it might mean. So you see, right now there's variation in each of these groups, right? And there's 1, 2, 3, 4, 5 people in each group. Now, we have an issue there with normality. We don't have 20 people in each group, so I would question whether this is normally distributed. But I'm not going to tell you how to account for that, so don't worry about it. And this is one of the problems I've seen in laboratory studies with ANOVA, is they haven't got sufficient sample size to account for assumptions of normality, so don't worry about it that much. Just be aware that it's something that we like to test for, even though we will not be testing for normality. Got that? So we have them all up. So group 1, the total number of scores is 15, group 2, 10, and so forth. And the mean, you can compute the mean, that divided by 5 people, so forth. Straightforward. Now the grand mean is going to be all these people added together divided by 15, or all of these 3 added together divided by 3. It's the same number, arithmetically. It should give you that, 4. Okay, if you don't believe me, try it yourself. Hopefully I did the math right. Sometimes I don't. Okay, with me still? Right on. Excellent. Grab me a 4. What do I do now? So the first guy here, he deviates from his mean by 3 points. That's his deviation score. Meanwhile, his entire group deviates from the mean group by 1. So his deviation is 3, his group's deviation is 1, his total variation is 4. That's just something to think about. That's how we're going to approach this. Each individual has a total variation from the overall construct. He has variation within his group, and he has variation between groups. So this guy has a variation of 4 overall, and so forth. Right? So we're going to compute the same thing for every person, but in a systematic way. And that's conceptually what this F-test is trying to do, is figure out a summary score for everyone's variation within his group and relative to everybody else. Okay? So let's do that now. So here are the mean of each group. Group 1, Group 2, Group 3, the means here. This is the grand mean, is 4, remember that. We're going to subtract this from the grand mean and we get these numbers. We're going to square those deviations and get these squares. This is the number of people in each group. I just multiply these last 2 together to get a sum. So this is the squares. These are the sum of the squares. So remember, sum of the squares? This is the first sum of the squares. The sum of the squares between groups is 70. Still with me, right? That's the easiest one to compute. Next, we're going to do the sum of the squares within groups. we have 3 groups, 1, 2, and 3. So for each one of these groups, I look at the deviation scores. So the first person scored 1, but the mean of that group was 3. That gives me a difference of 3. I square that, I get 9. Next person scored 6. The mean was 3. The difference is 3. I square that, and I get 9, and so forth. For group 3, the first person scored 5. The mean was 7. The difference is -2. I square it, and I get 4, and so forth. And I add up the squared sums of all of these, and I get this. So the sum of squares in the first group is 20, and the second group is 10, and the third group is 16. Right? Straightforward stuff. Grade 3 arithmetic. Still with me. Fantastic. I add them all up, and I get 46. So now I've got 2 numbers. I've got my sum of the squares between from the previous slide, and I got my sum of the squares within from this slide. I'm done. I'm ready to go, because my F formula is just that. And I plug in my numbers, and I get 9.13. What do I do now? I go to the back of the book, and I see if my number is bigger than the book's number. Right? And I find the book's number is 3.88. Is my number bigger? Yes, it is. So I do what? I reject the null, and I always answer the question. Reject the null, and therefore the mean scores are different between the therapy groups. I don't know which one's different. I just know they're different. Right? So we cannot conclude that each group's mean differs significantly in the group. Therefore, right. So that's what it all means. How can we test if one mean is different from the other mean? T-test. Okay, so I can do the one thing with SPSS. SPSS will do it automatically, and the printout looks like this. The F score is 9.1, exactly what we computed, and that gave me a p-value of 0.004. Is that low or high? Is 0.004 low or high? It's low. It's lower than what? 0.05, exactly. So the p is low, the null must go. Same conclusion, except I didn't have to go to the back of the book. It just gave me a p-value. So we compute p-values today because we have computers. This back of the book stuff, that's like what we did for the past 100 years because we didn't have computers. So we learned stats in high school. Oh, maybe your high school has computers now. I'm old, right? So yeah, you go to the back of the book. Oh, you look up. That's why we teach the back of the book method. Useful as well for conceptual thinking because you have to phrase an hypothesis and so forth. But these days we just plug it in the machine to get 0.004. Right. So I mentioned that the ANOVA that we're doing is a derivation of the independent samples t-test, meaning we're testing different people, different students in each class, different cars, each factory. But there's a version that resembles the dependent t-test, and we call that the repeated measures ANOVA. That's when I can test you 3 times. I compare your midterm mark with your exam mark with your final mark. That's 3 different things I can compare, but it's the same people I'm comparing. So there's some, problems there. We call that a repeated measures ANOVA. We will not be doing repeated measures ANOVA, but I want you to know that it exists and when I would use it. Okay, same thing. So if you're doing ANOVA and SPSS, as you will, just go through the slide. You can figure it out, and that's your homework. Dun dun dun. All done. Yeah, cool. All right. The looks on your face can't tell if you understand or not, so I'm going to assume it was crystal clear. All right.